Hello, this video is about the Nobel Prize in Chemistry for the year 1984, awarded to Sir William Ramsay for his discovery of the inert gaseous elements in the air and his determination of their place in the periodic system. Here we have the periodic system and the elements that we're talking about here in column 18, the so-called noble gases or inert gases, and you can see them here: helium, neon, argon, krypton, xenon, and radon, and this one is an official one. Okay, the name of the lecture is The Rare Gases of the Atmosphere, and it's summarized by me, and we're going to pass through it. In 1879, it occurred to me that an easy method of determining the volumes of liquids at their boiling points and consequently their molecular volumes would be to use their own vapors, coming from the liquids boiling under atmospheric pressure, as a means of securing the desired temperature. A simple modification of this plan was made possible to obtain a range of temperatures by altering the pressure under which the liquid boiled. This device led to a study of the critical phenomena of liquids for employing vapors as heating agents, and great uniformity of temperature could be secured. In this work, which was carried out from 1880 till 1887 with Sidney Young, the problem of the adiabatic behavior of liquids and gas suggested itself. The ratio of the specific heat at constant volume to that of the constant pressure, the specific heat at constant volume ratio to the specific heat at constant pressure, was measured in the year 1892 with Dr. E. Perlman. And it was only published in 1896, and the method employed that of Kundt and Warburg gave adiabatic curves for ethyl ether, both in liquid and in gaseous states. I carried experiments in connection with the combination of gaseous nitrogen with hydrogen and with oxygen, with the aid of platinum as a catalyzing agent. The results were negative and were not published. I read Cavendish's classical experiment on the subject, and it must have been the later memory of this which led me in 1894 to suggest to Rayleigh a reason for the high density which he had found for atmospheric nitrogen, being there's an extra gas in it. And that extra gas is argon, and argon forms no compounds. It's a noble gas or inert gas. Hildebrand observed that certain minerals gave off a gas when heated with dilute sulfuric acid. The gas spectrum showed certain unknown lines. I believed it may be a compound of argon, and the gas examined by Hildebrand was argon mixed with nitrogen. Examining the gas, a yellow line was observed. This line has first been observed in the solar spectrum by P.J. Janssen. Rutland and Lockyer suspected that the line was due to hydrogen, but could not prove that. Later, they concluded the presence in the solar atmosphere of an element unknown on Earth, and they called it helium. Here you see the experimentalist at work. Soon Langlet discovered helium independently. Helium and argon gas are soluble in water, not making compounds. Like argon, the ratio of its specific heat at constant volume to that at constant pressure shows it's a monoatomic element, the atom and the molecule being the same. Its density, found by Langlet and myself, nearly 2, thus the lightest gas known, except hydrogen, which has a density of 1. Helium and argon belong to the same family. There must exist at least 3 other elements of the same gas. Look at the periodic table. Maybe we should do that. You can see that helium was here, and argon is here, and the others were not yet discovered. But it was suspected that they should be there. Travers helped with the search. We investigated the gases involved from every mineral we had. Also, various materials were heated, the gases examined spectroscopically. We harvested gases from the Pyrenees, Icelandic, English and Scottish mineral sprints, and did the same with that, and about 4 liters of helium were prepared and fractionally diffused during about 3 months, hoping to obtain heavy fraction, the other gases. A similar set of diffusions was carried out with argon, and about 15 liters of argon was prepared with the intention of submitting it to fractional distillation, while Hampson worked in a machine for liquefying air. Minerals with urim and thorium yielded helium, but no new lines. The minerals Malacony gave argon and helium. With Cogoret, gases gave the same. Water from the bath springs contained neon. The fusion of helium yielded residue. With the lines of argon. Using liquid hydrogen, we cooled helium to a very low temperature. The condensed portion exhibited the spectrum of krypton. The diffusion of argon resulted in accumulations of 2 fractions. 50 liters of argon was purified, and Hampson perfected this machine, and it gave us 1 liter of liquid air. We allowed this portion to evaporate almost entirely to collect at least 10 cubic centimeters by allowing it to boil off. After removal of oxygen and nitrogen, remained 26 cubic centimeters of a gas with the spectrum of argon and lines of wavelengths of 5571 and 5078.5. Although the density of the new gas, renamed krypton, was found to be only 20.5, we considered that when purified it could be 40 times as heavy as hydrogen with an atomic and molecular weight of 80. It's the same because it's a monoatomic gas. Yeah. Here again you see the experimentalist at work. We announced the discovery in June 1889. No time was lost in examining the argon by liquefaction and fractional distillation. The lowering boiling portions of argon contained a gas we called neon. Its spectrum characteristic by a brilliant flame-colored light consisting of many red, orange and yellow lines. Its density is 13.7. We also believe to have discovered a second gas, meta-argon, but this was a mistake due to the use of an impure specimen of phosphorus. Kellis and Schussling determined the amount of argon in the air, 0.01183 by Schussling and 0.1186 by Kellis, and as a part by volume in 1 part of atmospheric nitrogen. The density of the purified argon was 19.95. The fractivity was 0.96 or 0.61, and September 1888 the discovery of another gas was announced, separated from crystalline by fractionization, possessing a still higher boiling point. We call it xenon. Travers and I prepared a purified larger quantity of the gases, while Bailey erected an apparatus for the accurate determination of the wavelengths of these special lines. We procured a Hampson's air liquefier and compressors. With the machine, air was fractionized to give us the gases to investigate. The air was liquefied and the nitrogen and the oxygen removed, leaving argon, neon, helium and other gases. The argon was separated by fractional distillation and the residue of crude krypton and xenon purified by repeated fractionization, tedious but not difficult. Otherwise, for neon, its separation from helium is not easy. Without the aid of liquid hydrogen, no further progress could be made. Travers and Holding constructed liquefying hydrogen apparatus. The hydrogen, after preliminary cooling with liquid air, entered in the chamber, in which air boiled at low pressure, at a temperature of minus 205 degrees Celsius. This is below the critical temperature, and it ran out in liquid form. The separation was effected in less than an hour. The neon became liquid and the helium gases. They are all monoatomic gases, proved by determining the ratio of their specific heats, their reflectivities, the densities and compressibilities at 2 temperatures, 11.2 and 207.3 degrees of Celsius. Again, here you see the experimentalist at work. For argon, krypton and xenon were determined vapor pressures, volumes at boiling points, critical temperature pressures. The gas show a regular graduation of properties, and they will fill the gaps in the periodic table below and above. With the atomic weight of neon 20, krypton 82 and xenon 128. Neon is contained in air in the proportion of 1 volume in 80,000, helium in 1 volume in 245,000, and not more than 1 20 million for krypton, and xenon for more than 1 part in 170 million. June 1903, Bailey published his determination of wavelengths of the lines of the spectra of neon, krypton and xenon photographed by help of a concave Rowland's grating of 10 feet radial curvature. In all, the position of 2,400 lines were accurately measured. The discovery that uranium emits rays was followed by the element radium in 1896 and 1898, and in 1899 it was discovered that beta rays in a magnetic field behave like cathode rays and have a large penetrating power. We now know they are electrons. Alpha rays have less penetrating power and they are defiable by a magnetic or electrostatic field. Rutherford was able to determine the electric charge of both particles, the same as hydrogen, which is +1. The beta particles were -1. He also determined the ratio of the mass to electrical charge of both. Thorium also proved to be radioactive. Air blown over radioactive specimens seemed to make the radioactivity stronger. Rutherford in study found out it was the alpha particle which has the same mass as the helium. Study found that the radioactivity of radium lasts much longer than that of thorium. Enough thorium was made to introduce into a measuring tube. It was found to be a self-luminous gas, obeying Boyle's laws, and its volume slowly contracted during 4 weeks. And on heating the tube, which had contained the gas, a gas was evolved from the walls possessing 3.5 times the volume of the emanation, which shows the spectrum of helium. By heating, a radium salt can expel the helium which has accumulated. With Collie, the spectrum of the radium emanation has been mapped. It resembles, generally speaking, those of the inert gases, and although its density has not been accurately determined, it appears to be approximately 80, which would imply a molecular weight of 160, and if it's a monatomic gas, its atomic weight would also be 160. It might then be an unstable member of the argon family. There's a vacant place for an element with atomic weight about 162. Of the rate of diffusion of the thorium emanations, we can now only say that it's high. It's still more unstable and might perhaps have the atomic weight of 250, for which there is a gap. It's not inconceivable that the more unstable emanations from the matter named actinium by Debierne and ammonium by Giesel may have an even higher atomic weight than uranium. Okay, again, you see the experiments as well here in a picture, pointing at the 18th column of the periodic system in which the gases he discovered are all placed. This was it. This was, of course, a summary of the lecture given by Sir William Ramsay and not a complete lecture. If you want to read the complete lecture, you can follow the link. Here, this one, for instance. And the link will also be placed in the description below the video. There's also a video about more general information about this Nobel Prize. Well, this was it. Thank you for watching, and next week we'll go to 1905. Again, thank you for watching, and maybe until another time.